Hi everyone, good evening.
Hi guys.
Hello.
Thanks very much for joining us. So 2 minutes past 7. I'll kick off with a little introduction and then yeah, whenever you're ready to go, Kris. So hi guys, my name's B. I'm one of the principal consultants here at IO. I head up our contract Java team. I've been here for about 3 years now. Ines, I don't know if you want to just say a quick word about yourself.
Yeah, my name's Ines. I also work with IO, work alongside B. I'm one of the business managers here, and I cover the Java Southwest space on the permanent side of things.
So yeah, I'm super lucky. Got Kris Foster joining us this evening from Oracle Labs. Kris, I don't know if you'd like to kind of introduce your talk and yourself, and then I can just go on to sort of how we're going to run through things this evening.
Yeah, sure. Hi everyone. My name's Kris Foster. I work at Oracle Labs in product management for GraalVM. I've done a talk here before. I was working in pre-sales then, again for GraalVM. So I'm going to talk about GraalVM and containers today, and why GraalVM Native Image could be a really good idea for containerized workloads. So it's all going to be from the command line, as you can probably tell from the first screen. There won't be any slides, but yeah, hopefully it should take about 45-50 minutes. Feel free to interrupt me and ask questions as I go. That's fine.
Amazing, thanks, Kris. I think if you're ready, let's just go straight into it, I think.
Okay, yeah, sure. So hi everyone again. I don't know if anyone's actually heard of GraalVM. I'm guessing you have because you've turned up for the call. So GraalVM is a Java runtime from Oracle, in fact, from Oracle Labs. It's basically 3 things. One is a new implementation of the JIT compiler inside Java. So we have GraalVM Enterprise Edition, which is like a highly performant JVM, gets better performance than C2 in the Oracle hotspot. So it's a really fast JVM. The second thing, which is the thing I'm going to talk about today, is our ahead of time compilation facility, native image. So we can take an application that's written in Java and we can turn that into a binary executable. So something that can run directly on Linux, Windows, Mac OS. It's got a number of benefits. I mean, the most obvious one of these is that startup time is insanely fast, and we'll see that as we go through the talk. It's got a lower footprint, so the amount of resources it uses in terms of memory is much lower. Again, I'm going to show you that as we go through the talk. And it's got other benefits as well. We have the ability to statically link libraries into the binary that's produced. So that means you can make a container that contains very little in it. There's no JVM, obviously, because we've just got this binary executable version of our Java application. We can get rid of lots of things. And I'm going to show you how to, I'm going to demonstrate, how to deploy in a Distroless container today, which is a very sort of slim cut down container with very few moving parts. So it's all going to be from the command line, and I'm going to switch between the command line and VS Code. So I've got a project here already, and I'll explain a little bit about the project, what it does, how I'm deploying things, and I'm going to go through a number of iterations of deployment. So we'll start off with our basic Java application, and we're going to see our Spring application, just have a look at the performance, measure those kinds of things. Then we're going to, Dockerize it and see how it behaves then. Then the next step will be to make a native image out of the Java application, and we're going to have a look at this. That's how that performs. And we'll do this sort of incremental approach. Each commit will take us to the next sort of optimization. So without any further ado, I'll show you our application. It's a Spring Boot application. I'm not sure if you know much about, I mean, I'm using Spring because it's the biggest framework really in terms of uptake in use in the Java world. It's really like high figures, like 70% or something of people use Spring, or not necessarily Spring Boot, but Spring. There's a project run by Spring, and which Oracle Labs is helping out in, called Spring Native. It's an experimental project that hopefully is going to get rolled into Spring, I think, like at the end of this year, and that provides support for deploying to native image. So it makes using GraalVM Native Image with a Spring application, relatively trivial. So my application, it's nothing very clever. I've just got an endpoint. So it's going to have like a web front end, a REST front end. I'll be able to call a URL and then get back some data. What does my application do? When this utility class over here, I've got the Jabberwocky poem. And I'm using a library called Rita that lets you build something called a Markov chain. It's a predictive model for some set of data. In our case, we're just going to generate nonsense verse based on the Jabberwocky poem. So when I call the URL, I'm going to get back nonsense verse that kind of looks like Jabberwocky. Any particular reason I've done that? I just think it's fun. So hopefully you'll like it too. And it's nice and self-contained. I think with a lot of these demos, everyone's always pulling in databases, this, that, and the other. It's nice if you can like keep the number of moving parts down to the simplest, so you can focus on just the bits that I want to talk about. So don't really need to go into that too much. It's built with Maven. So if I go over to my terminal, I can have a quick look. I've got all my code in there. So I can build this application really easily with Maven. So let's just do that. And then we're going to run it and then call the endpoint just to demonstrate what the application does. So this will take a second. Can you all hear me okay? And like I said, please don't worry about asking any questions or interrupting me, correcting me, anything like that's totally fine. So that's built. In my target directory, I'm going to have, so I've got this executable exejar, because that's where I'm creating a single executable, single jar, with everything in it. And it's got manifest, so I could just launch it with Java jar. So I'm going to do Java jar, and then the target directory in Jibber, I think I called it. And I'm going to put it into the background. So that's going to start up, and we can see all the standard Spring logging coming to standard out. Okay, and we can see the startup time started in 1.693 seconds. So easy enough to call it. I'm just using curl. It's running on port 8080, and I think I've got this right. Brilliant. So this is my endpoint. I called my endpoint localhost 8080/Jibber. And I got back some nonsense text that kind of looks like based on the Jabberwocky poem. And each time I call it, I should get something back that's slightly different, but still like the Jabberwocky poem. So that's our basic use case. I'm going to pretend that's like my microservice. I'm selling rubbish verse to the internet through this wonderful API that I've built. So not very interesting in itself. What would be good is like if we can containerize that and start it up and maybe get some monitoring stats, etc. from it. So if we go back to our editor, I can show you in here I've got a Docker file based on like OpenJDK from Oracle Linux on Oracle Linux 8, and this is from the Oracle Container Registry. So a bit like Docker Hub, we have our own container registry. And it's a very simple thing. You pass in the name of the jar file, you copy it from the build directory into a Docker file, you give it an entry point and a command, boom, boom, boom. And so then we can Dockerize it. So because I'm lazy, I've written a script that will do this for me. It will build things, it will tag it in a way that I'm expecting. So let's run that now. So my script is called step 0. You can see where I'm going with this. There's going to be a step 1 and a step 2, and who knows, a step 3. And then I kind of went off piste as I was writing this, and I started calling them step something else instead of a numeric number. I'm not quite sure why I did that. Kind of broke the thread of the whole thing. So that's built now. And if I just do Docker images, I don't know, last 5. So we can see 30 seconds ago, my JDK container has been built with my app in it. So I can run that. I could do Docker run, but again, like I said, I'm kind of lazy. So what I've done is I've got a Docker compose file. For those of you who haven't used it, it's just an easy way to spin up lots of containers. And as I go through this lab, I'm going to package the app in a different container each time, but I want to keep the old container running. So Docker Compose is a good way to let me say, bring up the container with OpenJDK running my app, bring up the native image container, bring up the next container. And then when we're pinging them and getting some stats from them, we can kind of correlate those and display them all together at the same time so we can get an easy comparison. So there's not a great deal to this. We just say, I want to use the container that I've just built. We put some controls in place, like I'm going to limit the memory. I customize it a little bit so that I can set the heap size. And I've also got Prometheus in there because later on, I'm going to start pulling in information from the container, like the resident set size, the working memory of the app, which is going to be interesting to compare, like, what the Java container needs in terms of working memory versus what native image needs. And also I'm going to look at JLink as well, which is another option for shrinking things. So if I can bring my containers up with this Docker Compose command. You just tell it up, which means bring everything up, and -D to put it in the background. So that's going to start my containers. Brilliant. And I could call them using curl, but I've written some stress testing scripts that basically do this and display some nice information. So if I call stats, it's going to print these nice little bar graphs that hopefully like tie all this information together. So the first thing we're looking at is the container size. So our jar file is about 21 meg in size, is 21 meg in size. Our JDK container is almost 600 meg, so it's quite big. I mean, we know we could shrink that, but just as a kind of a basic starting point, it feels about right. Then we're going to run our application and pull some more information from it. So the startup time, which I get by querying the logs for the Spring Boot process, because when Spring starts, it tells us what the startup time was. So it's about just under 2 seconds. And then we do some stress testing. So I use a tool called Hey to hit these endpoints and query some information. So the kinds of information that's interesting to me anyway is like the latency. So 95% of all requests that hit the server responded within 4 milliseconds for this API, which is nice. And then also the throughput. So how many requests per second, kind of averaged out, slightly extrapolated, can this handle? So just over 1,000. And I run that a couple of times just to check that the results seem meaningful. And we get very similar kind of figures for each time. So that's our baseline. So we understand now, what's the kind of performance we can get when we deploy our application to an OpenJDK container. It's quite a mouthful. So that's step 0. That's our baseline. So the next thing we'd like to look at is, let me kill everything. The next thing we want to look at is using GraalVM Native Image. So I'm going to switch to the next branch, and that will update all of my files, and then we'll go through those files, and then we'll start everything up. So we're going to switch to, I think step 1, right? We're going to switch to step 1. Help if I could type. Okay, cool. So now we're on step 1. If we go back to the editor, if I talk too fast or if I'm, going too fast, please do say. Our app hasn't changed. What's changed? Well, the first thing is we've got some additions to our POM file. So let me find my POM file. So I'm building all this with Maven. Most of this is pretty straightforward. There's just some dependencies, all the dependencies I need, which I haven't shown you inside the POM file yet. We pull in, Spring Boot. We also pull in a couple of things such as this is the Spring Native stuff, like the AOT Maven plugin. And you don't need to know this. You can go onto the Spring Starter, like the website, and say, as one of the things that you want your Spring Boot application to have is native image, and it will auto generate like a POM file for you that has all of these dependencies in. But you need to be aware that you need to add these at the moment in order to make use of the native image integration with Spring Boot. So when we built it, when we build it, I'm going to use a profile. So in Maven, you can use profiles to kind of have specialist builds. So when I type Maven clean package, it will build the Java app. But when I type Maven clean package -p for profile native, it's going to trigger this. And what it's going to do is build a native image. And this uses our native build tools plugin for Maven that lets you pass through information such as the class path. It makes using native image quite easy. It passes the class path and various other things like that through to native image, but still gives you the kind of flexibility to specify certain parameters to the native image build. For instance, I can say what I want the output file to be called. I can pass parameters to native image. So I want to see, exceptions. If there are any problems, I want to make sure the exceptions are reported to me. But I guess the best thing to do now is just quickly to build that. So the way I actually am using like Maven here, I've moved on from this now. I'm tending to use the Spotify plugin to build based on a Docker file as well to make an image. But I haven't updated this lab yet, and that would be a kind of a more clean, nicer way to do it. So hence the need for Maven, my build scripts. So anyway, we're going to build this. And you can see that it's kind of changed. There's a lot more information. And we can see output from native image here, GraalVM Native Image. So the kind of steps that you see when you run native image from the command line, like independently, you also see in the output from the Maven build. And native image takes a little bit longer to build. It's kind of a trade-off, really, in some ways. You get a slightly longer build time, but your startup time and your memory consumption, trading time at one end for time at the other, if you see what I mean. There is a way now with the latest release, we've got a quick build mode where you can turn off all kind of inlining optimizations and it builds much, much faster. So when you're doing development, if you want quick native image builds, that's now a possibility. So this is probably going to takes about, I think, maybe 50 seconds, a minute, something like that. Almost done. Creating image. And at the end of this, we'll have this, there we go, we'll have this binary executable. So if we have a look in our target directory, we've got this Jibber exe. And that's just something I can, and that is our app, right? I can actually just run this. It's a Linux executable. If I run it now, we can see, something's already running. I wonder if I forgot to, yes, that always happens. Busy talking and not paying attention. So let me run it again. So I've run my executable, and this time we can see it started up much, much faster, right? It started up in like 0.037 seconds. So much, much faster. But we can call it in exactly the same way, and it should respond in the same fashion. I've got that right. Yeah, so look. So I'm going to bring that back to the front. So what have we actually done there? We've taken our Java application and generated like this Linux executable from it. And it is a Linux executable. Yeah, it is a Linux executable because I can do LDD on it. And I can see what libraries it's linked against. I could do other things like, look at the object file and see what's in there. But it's not a Java application. There's no JVM baked in. It doesn't rely on there being a JVM present. That's the key thing. So we're going to build it again because of the way I've done the scripts. I'm going to build it, but this time I'm going to build it from my shell script, which is going to package it up as a Docker file. And whilst it's building, I'll show you the Docker file and just how simple that is really. So now we've got this new Docker file, dockerfile.native, right? This is just based on Oracle Linux 8 Slim. So it's the Slim, it's basically just an Oracle Linux container. It takes an argument, what's the name of the executable file? So that's what we're going to copy in. We copy in the executable file and we just say run it. So it's really, really simple. So we'll go back and it's still building. Actually, whilst that's building, I can show you my Docker Compose file now. So now I've got my original Java container being started up, but at the same time now, when I do Docker Compose up, I'm also going to start up my native image in a container. And then we'll run the stats script again, and that will this time pull in information from both of the containers and show them side by side. And if you're interested, how I'm getting those bar graphs in shell script, it took me 2 or 3 days to find a really good solution. But there's a nice tool called Term Graph. It's a Python tool, and it lets you display bar charts in the terminal. So yeah, it's worth having a look at. Yeah, and I've constrained the memory slightly differently here. I've given my native image container, harder constraints. I've halved the memory, given it the same number of CPUs and the same heap size. So I guess what I'm trying to show here is that we should get, similar performance, maybe better sometimes, but the resource utilization will be less and it will start much, much faster. So it's kind of ideal for cloud-based stuff, because in the cloud, you're going to be paying for CPU and for memory. So, okay, that's done. It's built. So again, if I do Docker images, I don't know, 5. Let's see. Yeah, so I just built that 50 seconds ago. So it's my Jibber app tagged with native. So let's bring up my application. Okay, so now if I run the stats shell script, stats. So we've got some more information here. So we've got our original jar file, which was 21 meg in size. Then we've got the size of our native executable. So that was the Jibber file in the target directory I showed you. That's about 82 meg. Then we've got the site. So that's much, much reduced, right, from the Java size. But I'm going to show you how we can shrink this down to almost 100 meg in size. In fact, really, we could probably get it down below 100 meg in size. And then we can see the startup time of the app. Well, the native image container, the application in that started up in 53 milliseconds before that, first useful request. The JDK container was in 1.82 seconds, so sort of similar time to before. And then we get to our stress testing. So looking at the 95 percentile for latency, so 95% of your requests are within this time. So for the native image, we've got 8 milliseconds. So and this time JDK about 5. So it is in this instance, the latency isn't as good, but we're going to look at how we can improve that. Requests per second, not too different. Native image weighing in at about 1,000, JDK container, 1,140. So it's getting quite close to the same kind of performance. But as you'll see, I'm going to click on this link I've embedded here. This will take us to Prometheus, a Prometheus graph. And here we can see the blue line is the memory consumption, the resident set size for our native image. And that's really low. What is that? It's slightly over 20 meg here. And here we've got, 140 meg for the OpenJDK container. So in this instance, I'm not saying all your apps are going to be running in 20 meg. I mean, probably it's more likely, 80 to 100, maybe a bit more. It depends what your application's doing, what's in what's loaded into memory in terms of code as well. But you are likely to see, a significant reduction in the memory consumption for native image, and the reasons you're going to see that memory consumption reduction is that there's a lot less in the native image. Firstly, there's no compiler. Everything's statically compiled. There's no cache of the bytecode. We're not using memory for compilation. There's a whole host of things that are now happening at build time that don't need to happen in the JVM. And one of the reasons I suppose that Java had all of that originally was because it was write once and run anywhere. So the whole point of bytecode is that it's platform independent. You take your bytecode, you can run it on the JVM varies right from machine to machine. So you can run it on your Windows box on top of the Java installation there, and it'll work fine on Linux, on Mac OS. But in the cloud, really, it's kind of homogeneous. you know everything's going to be a kind of some form of Linux server, but you also know in advance what you're targeting, right? And when you make those decisions, you're typically targeting like a kind of homogeneous stack of Linux boxes or like Linux ARM boxes, typically. So, you know, you can, if you think about it in that way, you can actually get rid of that. The other benefit of like the bytecode and the compiler is the just-in-time stuff. You know, being able to adapt to the data that's flowing through the application to make assumptions about the code base that produces this highly optimized native code. Well, you can't do that if you statically compile your code, which is what we're doing. You know, you do that at build time, but we've got technologies which we'll see later on if we've got time, called PGO or profile guided optimizations, that allow you to profile your application in the same way you do with the C application, right? You can profile a C or a C++ like a native application, gather profiling information and use that in your next iteration of building. Well, we've got the, you know, very similar technology in native image. So that was our next step. So we've done step one. And just to recap, we saw that we had smaller containers, faster startup times, you know, much reduced memory, kind of similar performance. Not as good as OpenJDK, but similar. So let me kill everything. Please, this is be like the pantomime. You can shout out like he's behind you or something if I forget to kill things. Yeah, okay. Did I? Oh, no. You see, you weren't helping me. I needed to say that. Docker compose kill. Okay, so let's do the next bit. Get branch. So we're going to look at step two. Right. So what's in step two? Let me clean the screen first. So we've changed things a little bit now. So what we're going to have this time is going to have our OpenJDK container, like our native image version of the app. And then we're going to look at adding G1 support to the native image. So in native image, say community edition, you've got a relatively simple garbage collection, like garbage collection utility. We've got a serial GC. So you get these kind of stop the world pauses, and you will see like a slight offset. You'll see two peaks in your latency graph, for instance, because when GC kicks in, there's a pause, cumulative pause that adds up for requests whilst GC is happening. And then GC stops. And so if you look at a latency distribution, you will often find like the peak latency and then a slight offset, another little peak. Not always, it depends on your app, but you get these kind of offsets because GC is happening. With the Enterprise Edition, which is like the paid version, basically, if you've got a Java subscription, it's free for development or evaluation. It's free if you use our cloud or if you have a Java subscription. We provide G1. So it's the G1 GC from hotspot runtime that's been ported into native image. So I've got scripts, etc., to build all of this, and I'm doing it again through profiles in my POM file. Wish I'd found my glasses. There we go. That's my POM file. And the key thing here is just that it's really easy to use. I've got in my profile now, I've just got a flag that I pass through to native image --GC that tells the native image tool what GC to use when it's generating the native executable. So you have to tell it at build time. You can't switch the GC at runtime because the GC you select will get baked into the executable that's generated. So with the Java application, you can tell the Java runtime to switch between, you know, I don't know, ZGC, you know, G1, something like that, Shenandoah. Is it Shenandoah? Yeah. But that's because you know, the platform, the JVM has all of those available to it. With the native image, the whole kind of spirit of this is minimalist, right? So we bake in just what we need. So we're going to tell it we want the G1 GC. There's another one. We've got like something called Epsilon GC, which is no garbage collection at all, which sounds like it might be a mad idea. But if you've got like short-lived command line applications, and you know, maybe you don't need GC. You know, maybe you can just like allocate memory. It dies. You know, everything's cleaned up. So you don't need this sort of periodic garbage collection. So let's build. No surprise. No prizes for guessing what my shell script is called. So we're on step two now, aren't we? Yep, step two. So if I do this, it's going to just call, as you can see, the container I'm building is the native G1 one. It's going to take a little time to build, probably about 50-60 seconds again. And at the end of it, and you can see that we're like now when we're doing the build, you can see that it's baking in the G1 GC. So there are 5 native libraries that are being referenced as part of this build. One of them is the G1 GC library. And that's information coming from the native image build. It seems quite slow, I suppose, this, doesn't it? Because we're used to sort of much more rapid feedback, but there's a big sort of push to try and improve the build time for native image. One way to think about this is kind of like it's an optimization step. So you build your Java application, you test it, debug it, play with it as a Java application. You know, when you're thinking of deploying to production, or, you know, that's the kind of stage you want to start looking at native image. Maybe if, you know, maybe earlier on as well, just to check that, you know, there are no issues with any libraries that you're using. Okay, so, but it's really kind of an optimization step. So it took, how long did it take? Yeah, okay. So in user land, it took, you know, oh no, where did I see the time? Yeah, okay. So we've built our container. So now I can do Docker compose up, and it's going to launch 3 containers, my OpenJDK one, my native, and my native G1. So there we go, and my Prometheus, which is C advisor for capturing information. So let's run our stats. So now we've got our G1 executable. You can see it's got bigger. So the previous native executable was 82 meg in size. This is 112. So that's because we've baked in more. You know, we've got like the G1 GC in there. The startup times are about the same for the 2 containers. You know, in and around 30 to 40 milliseconds. Now with the latency, the G1 has done much better. I mean, your workload will vary. I mean, mine's, you know, it's kind of sort of self-contained, different workloads, you'll see different things, but it shows you that, and look at the throughput as well. For this particular application, the throughput is better than the OpenJDK container at the moment. I mean, it gives you different choices, right? I'm not saying it's always going to be better, but it's also not always going to be worse as well. Like, you know, it can be significantly better. Sometimes switching on G1 GC isn't the right option. You know, using the serial GC may be right. Depends if you care about latency or how your application is used. So there's there's various different things to think about. And if we look at the Prometheus plot for this, now we've got another line on here. So this one at the bottom, I'm thinking is the pure native image. Yeah. So this red line with really low memory consumption, what's that, about 25, 30? That's our native image. With G1 GC, it's using more memory, 80 meg, but it's still significantly less than the 140 for OpenJDK. So let's go back to this. So we've added like one level of optimization. We put a different GC into our native image. We've seen that the container size got a little bit bigger, but it's still significantly smaller than the OpenJDK one. We've still got the great startup times, like milliseconds versus, tens of milliseconds versus seconds. And we've got better performance in this scenario, but with less memory usage, much less memory usage. So I'm going to kill everything. Compose kill. And we're going to jump onto the next bit. This is, guess what that's called? Step 3, yes, don't all shout at once. So what have we got in our setup now? So if we maybe start with the Docker Compose file. So again, we've got our OpenJDK container, our native image with G1, and now we're going to look at Distroless. So Distroless is like a minimalist Docker container. I think it's about 20 meg in size. It contains very few things, basically. It contains some certificates, some basic files needed for an OS. It contains glibc, a standard C library, the GNU standard C library in it. But I don't think it contains anything else. It's like really tiny. I know Alpine's another option in this space. I'll talk about that at the end, but we do support both glibc and libmuscle. So if we have a look at our Docker file for this next container, so I've got one called Distroless. I'm just going to build off Distroless, but apart from that, it's exactly the same. I'm going to copy my native executable into the file and just say run it when you start the app, when you start the container up. Again, there won't be a surprise that I'm using a POM file to build this. The key thing to call out here is, in the same way that, like, to native image, I can pass in standard native image flags. So I've got my G1, GC flag, use G1 for the garbage collection. But here I've got an interesting flag. I've got static executable with dynamic libc. So this lets you build like a mostly statically linked executable. So it'll have any libraries, like system libraries it needs. They will be statically linked into it, i.e. made part of the executable, apart from libc, which will be dynamically loaded. And that works fine it works really well with Distroless. You can do fully statically linked, and that means you can use a from scratch container with literally nothing in it. But then you do have to package things like certificates, etc., possibly, and some other files if you need them from the Linux distros. What is there to say about the differences with that? The benefit of being completely statically linked, I think, is in terms of security. The less you have in your container, the less of an attack surface there is for it. So if you have, like, say you need a shell prompt in there, if you need this, that, and the other, the more things you have in your container, the more chances that it is vulnerable, the more things to patch, more potential weaknesses. If you've just got your binary file in there, it's a very secure API, right? It's just got this one. You've got any vulnerabilities you had anyway with your other containers, but anything else is all stripped away. Because when I say with your other, you've got only the vulnerabilities that are like baked into your application. Everything else is got rid of. But you would have had those vulnerabilities anyway, right? When you were deployed with a shell, with glibc, with this, that, and the other. The other thing to bear in mind with this is that, like, the difference between glibc as a standard C library and libmuscle as a standard C library, when you're using glibc, we only support currently, and we only ever will, I think, support mostly statically linked. So that means you can statically link everything in apart from glibc, and this is because glibc has a very old now defect that relates to basically it being expecting to be dynamically loaded. So when you start to use anything with the network and you start to do DNS stuff, namespace lookup, there's an issue. And that's because the way that code is written inside glibc, it kind of expects to be loaded dynamically, otherwise it doesn't work. Libmuscle, on the other hand, if we use the libmuscle toolchain to build our executable, we can create fully statically linked executables, because libmuscle, as far as I know, in fact I'm certain of that, is fully capable of being statically linked into your executable with no issues. I haven't got an example of this here, so that's why I'm doing like the static executable with dynamic libc. So this is the option if you want mostly statically linked, but you're using like a GNU libc distro. That was kind of a long little discourse, but I think it's kind of interesting to know like the differences between the two kinds of distros and how we support them. So we've got this extra flag. So let's build this. So I'm on step 3, right? So I'm going to run my build script. This is doing the Maven clean package -p with whatever I call that profile. I guess it's Distroless. So it's going to build my Distroless executable, and it's going to package it in that Distroless container. So this will take a little bit of time. Unfortunately, I spent ages. I should have kicked this off in the background whilst I was rabbiting on about the different kinds of static linking we can do, and then you wouldn't have had to wait. But again, I suppose it only takes 30, 40 seconds, so it's fine. So when this is done, we'll do the same thing we did before. We'll use Docker Compose to bring up all our containers. So all the ones we've done so far, plus now our Distroless container. And again, they've all got the same, exactly the same application baked into them. And we'll run our stats like shell script just to see how they compare, how these different versions of the app, different ways of deploying the application compare. Almost there. I need some sort of music or something, don't I? Perhaps a potter's wheel, or there we go. Yeah, okay, so it's building the Docker file now. Okay, it's done. So just better check I've not got loads of things running. No, okay. So now if I do Docker Compose up, start all my things. Okay, and I run my stats shell script. So again, we've got this progression from like the size of the jar, and then over here we've got our Distroless container. Our Distroless container. That's 138 meg in size. So it's a lot smaller than it kind of went up to when we were using G1. So we've got rid of a whole lot of stuff, and the stuff that we've got rid of there is most of the Linux distribution that was in the Oracle Linux Slim. We've still got our glibc baked in directly into the native executable, which is why that's actually I haven't actually included that in there, but that will be bigger than just the G1 size of the executable. The startup times, okay, they're all similar. I think, you know, any difference here probably could be noise. Let's have a look at the latency. I haven't really done anything with the latency in these figures because it performs in exactly the same way as the G1 version, because like the dynamic linking and the static linking, the dynamic linking happens, you know, it gets linked in at the startup of the application. So it doesn't really affect the performance of the application. The key thing here is just that the startup time hasn't changed and the size of the container has gone down 138 meg in size. So we've gone quite a long way in like shrinking the size of our container to a more manageable size. So let me kill everything. And then we're going to look at next. We're going to look at JLink, because I don't want to be unfair, right? I want to show, you know, there's a tool in, you know, I think it's Java 11 plus called JLink, where you can make minimal versions of the JVM and distribute your application with that. So why don't we have a quick look at that? Because I've made a version of the application that works with JLink. And if we go over to our Docker Compose file, as you've seen before, we've just got one more thing at the end, right? I've added another container I'm going to start up. This one's called JLink. And if we have a look in our Docker file for the JLink one, and no surprise, my build script is going to basically just build it with a profile and then package it up inside this container. We're using JLink to link in only the modules that I know I need to get this app running. And that's inside our builder. And then we're going to, and then we copy that minimal runtime JVM into this container. And then we copy our target jar file in, our jar file that we were running in the same way as we were doing before, and that's a parameter to the Docker file. We add our JRE, our new minimalist JRE, to the runtime, and then we start Java up. So let's see how this performs. So I think, what did I call it? JLink. Yeah. So let's do our JLink build. And out of interest, it's about a month or so since I wrote this, so obviously I can't remember how I did it. How did I did I use I don't think I actually used a profile. No, I don't need to, because it's just the jar file. So, okay, that's run really quickly. Now, if we run our stats command, again, the only thing I'm really interested in is the size of the container. The JLink JVM is going to perform the same as like the normal JVM. It should just be smaller. Oh, I didn't start anything up. You were supposed to tell me when I did something like that. Okay, so let me start up all my containers. Okay, so the JLink container is shrunk. So our Java distro, which was, our Java container was about 600 meg in size. But when we switched to using JLink, we've managed to shrink it down to towards 200 meg in size. But that's still significantly larger than what we could do with Distroless, right, and native image. It's almost like 100 meg smaller. And I think realistically, I think we could push this further down as well in size. If I got rid of G1, GC from in there, if we didn't care too much about performance, that would probably, that would take out, what's that going to take? It's going to take out about 30 meg. So that would take it down to about 100 meg in size. And then if we look at the performance, no surprise, it's kind of the same, for JLink and the Open JDK. But the key thing is that, if container size is something you're interested in, there exists a technology, JLink, with the JVM that lets you make these minimalist JVMs. It's a bit of a guessing game, or I certainly found it was, to know exactly which of the they're not called modules, aren't they now? Which of the modules you need to have included in your JVM to get your app working. And the way I kind of figured this out was just running something and seeing when it exploded, and then digging into what module was needed. But once you figure that out, you don't need to do that again. It's going to be the same for kind of all flavors of the application that you have that are very similar. So we've seen that we can shrink things with JLink, but not as much as we can with native image. And then the last thing I want to show you is PGO, Profile Guided Optimizations, which is something I alluded to at the start. So if we okay, I'm just going to start the build script up whilst I'm talking, because I'm sure you're bored of watching the build script. So I'm going to do that, and then I'm going to go back to my app, and in the Docker Compose file, kind of no surprise, we've now got another container, and this is our optimized one. So this is going to be the native executable that's going to make use of profiling information. And I'm going to talk about how we, gather that profiling information, how we use it. I've already harvested that profile data, and we're using that in the build to make an optimized native executable. It uses the same Docker file basically to package it. There's no difference there. It's just a different executable generated. Most of the key differences now are in the POM file. So again, I've got different profiles here. I'm using a profile to instrument my native image. So the first step is to capture the profile information. And how do we do that? We do something that's called, we instrument the native executable that we generate. So when that native executable runs, it captures profiling information. So, what objects are created, how things, what things link to other things, frequency information, that kind of stuff. It dumps that when you kill the executable as this massive JSON file, usually called default.iprof. And to create one of those, when I build the native executable, I just say that I want it PGO instrumented. So when it runs, and I run it against like a kind of a typical, like a representative workload, is probably the best way of describing it. Run your app. You could run your app kind of in like A/B type scenario in production, or you could capture some data, or you can have some unit tests, or some kind of test suite that represents the data for your application. You run it against your instrumented native image, your native executable, and when it dies, it will create one of these profile files. And I think I've got it here somewhere. Yep. This is massive. It's probably may just have killed my editor. Maybe I shouldn't have. Oh no, there we go. I didn't. It's okay. So you can see it's just like tons and tons of information about what's happening inside the native image runtime, right? What types are available, etc. And then to call it, to actually make use of that profiling information, again, I've got a different profile for doing this. When I build now, I can tell the native image tool that I've got this profiling data. So it's pretty simple. I just pass in another flag, --PGO, and then the location of the profile file. If you're building inside of Maven, this always catches me, or caught me out a lot at the start. You have to use project-based dir. Otherwise, if you do anything silly like /default, the name of the file, it looks in, I can't remember where, either your home directory or somewhere. I can't remember where, but it's not where the profile file is. So I always forget this. Basically, you have to use this variable project.base.dir, so which gives you the base directory for where the profile file is captured. So I'm building this, so hopefully this might be done. Yeah, so I've built my next binary. I've captured the profile information, and I've used that profile information with the binary. So we should hopefully get an optimized binary, optimized for performance, right? Because there's different ways you could optimize things. And we're going to start up all our containers. We've got loads of containers now. I'm going to run my stats, and let's take a look. Okay, so one thing that is quite interesting, the container size is really small. So from the profiling information, obviously we were able to use, the compiler was able to make some like heavy optimizations that got rid of things. That doesn't mean it's removed things that you could potentially use, but it's structured or inlined or done some funky compiler stuff in a way that has reduced the size of the binary, obviously. The startup time, I think that is slightly faster. But again, it could be noise. There's not much in that. It looks better on this graph because like displaying that in the terminal, there's no way to kind of correctly show the right number of pixels there. But it's a similar startup time to the other native images. And then I've only done one round of testing here. But if you look at the requests per second, you can see that with PGO, we've got we were able to handle a really high number of requests per second, like 2,000 requests per second. Again, this is from this Hey tool that I'm using, command line tool, that lets you stress test, HTTP endpoints. I ran it again, kind of similar kind of figures. And then if we look at the memory footprint, so it was 2 secs. So again, up here we've got our JDK, and we've got 2 here. So that's M1 and PGO. So they're about the same. So it hasn't, in this case, it hasn't significantly increased the memory. So not quite half in this scenario. The memory consumption isn't quite half, but we've, got twice the throughput, for instance, and our container size is significantly more than exactly half the size of what we could achieve with JLink. So smaller containers are faster. They're also going to be more secure, as I said, because there's less in them. And the startup times are like, a factor of, I don't know, what, tens of milliseconds, like 100 times faster. So there's a lot to take in there, but I mean, it's an interesting choice for deploying applications in the cloud. And if, obviously, if you're building command line applications, native image is a bit of a no-brainer because it's easy to deploy the application, right? You've got a single binary and the startup times are going to be ludicrously fast. And you typically care about startup time with a command line application. But in terms of the cloud, the story about the cloud is that this is a more efficient way to deploy your applications, your Java applications in the cloud. So a lot to take in there. Anyone got any questions? Stunned silence.
Thank you very much, Kris.
No worries.
That's brilliant. I was wondering what the major kind of limitations of GraalVM are. Are there any big downsides that haven't been mentioned?
Yeah, so with GraalVM, it is quite a different technology. We're now at like high 90s, I think, passing the JCK, the Java Compliance Test Kit. but it is different, and it was made for different reasons. So we have this at the core of native image is this kind of like parsimony. You know, we want to use less resources, and we want to, you know, get rid of code, eliminate dead code, and the motivation for that comes out of the fact that it was originally a way to bake the GraalVM multi-language features, which I haven't talked about, into the Oracle database. And if you obviously bake a product into the Oracle database, they're very, 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 you know, like not the kind of software I like to write. Very strict guidelines about, you know, memory consumption, response times, you know, how many threads you can use, etc. So in order to do that, they took an approach of what is called like the closed world assumption. So with native image, we assume that everything at build time, at this separate build time, so this compilation time where we build our bytecode, then you could just run your bytecode on a JVM. But with native image, there's this extra step, this native image build time. At that point, we assume that every class that is reachable is available to us, and we perform static analysis. You know, so we look at everything. So as typical Java library, you might use like, you know, I don't know, field line left or something, but you might bring with that like tons and tons of stuff. Like you might bring in the Apache Tika project to left align something or extract a text string. I've seen lots of examples of things like that. With native image, if we can prove that you don't use it, it goes. Right, so we don't include it, which makes your application smaller and faster. But the flip side to that is that Java is also a very dynamic language. You know, so you can do reflection, you can do class get by name, you can do all these kinds of things. And native image, you would think, wouldn't support that. So this is like one of the limitations. It's like ahead of time compiled, right? So we have to know the state of the world when we're running it, when we're building it. But like it was realized earlier on that people, you know, might want to just take any Java application and run it on top of it. And so they came up with a way to gather this information. So we provide a Java agent. So when you run your application, you can capture in various JSON files, you know, any instance of J and I, any resource class, any resources that have been picked up from the class path, you know, any instances of reflection, serialization, etc. It will gather all of that information, but that relies on you having a complete test suite. So that does generally work quite well, right? But it requires thorough testing. But the flip side to that is that technology for providing the configuration for this dynamic features, right? It's like the code plus what's going to, you know, configuration for what could happen dynamically. Library authors are now providing that as part of their distribution. So if you look inside some jars for you know, libraries that say they work with native image, there'll be a meta-imp / native image folder as part of the jar, inside which you'll see these various JSON files. And you can layer native image will any jars that are loaded onto the class path, any of these layered configurations will be added together cumulatively and used to inform the native image build tool about all of this dynamic stuff. And if you use some of the tooling that comes with the frameworks that are supporting it, so like Spring Native, for instance, they're putting a lot of effort into making sure that anything that works with Spring, like, you know, any of the standard stuff, or Micronaut, for instance, is another one that's very focused on this. They're ensuring that any of the things that, you know, they say work, any of the, I don't know what you call them in Spring, but like the framework plugins, so if you want to use Kafka or you want to use JPA or something, that they all work with native image, and you don't need to do anything else than just add something to your Maven file. And that was that AOT, one of the things anyway, that AOT plugin that you saw in my POM file. It's doing a lot behind the scenes. It's fixing up certain classes that need fixing up, you know, creating substitutions, but more importantly, it's providing configuration for lots and lots of Spring dependencies. The other option is that, you know, this is the one that Micronaut have taken, and I quite like Micronaut. They instead of being dynamic, so a lot of Java is, you know, annotation based, it's declarative. You know, I say I want to do some, I like, where's my REST point? Let's have a look. So in my Spring, is it there? No, it's in here, sorry. In my demo application, I define that this is a REST endpoint by just saying an annotation, request mapping. This maps, so the path /Jibber maps to this method. And when I call it, this is going to give me back some sort of HTTP thing I can make sense of. This is done dynamically, right? But it could be done like at build time. So that's what Micronaut does. Their annotations are handled by what they called annotation source. The name eludes me at the moment. But basically, they're handled as part of the Maven build process. So when you build your application, the annotations are done like at build time. And there's a lot that we do in Java typically, runtime through annotations and reflection, etc., could really be done at build time. And in lots of ways, you're going to see improved startup performance, right? Because that task happened once, and it's like mapped to an actual type, or at least a method that dispatches to a known set of types, like when you built your application, rather than scanning the class path and trying to find things and then getting all the kind of errors that you get, like, oh, this jar's on here, now it behaves differently. I mean, it's horses for courses. Some applications, you want that level of dynamicity, is that a word? But if you're building an editor, you want to be able to drop something in and hot reload, but for a whole class of applications, you don't. So I think it's about choices, right? That was a really long answer, I'm sorry. I wanted to make sure I was saying the real truth, unvarnished truth. But
thank you for that. It was a very long answer, very thorough. Thank you.
Yeah, so there are limitations, but we can work around almost all of them.
But there's no major kind of repositories or anything that you can't access using a native image. There's no libraries that support. There's always a library to support MySQL or Redis or Mongo or. Yeah, for most of it seems, right? So I think it's how much do you want to stick to the beaten path? If you're using Spring and you're using, their plugins, I don't know if that's the right term, but then yes, if there is an issue, someone will fix it quickly. You need to just raise a defect because it's on the agenda for getting fixed. If you use Micronaut, the same kind of thing. If you use Helidon SE from Oracle, then the same kind of thing. To say that there's not libraries out there that don't work with it wouldn't be true, right? Because there's 25 years worth of people writing libraries in Java. I think it depends. Some of the XML stuff sometimes can be, when XML was all the rage, there'll be some very, very dynamic stuff happening there. And watch out for things like ByteBuddy. But even ByteBuddy now, the later versions of ByteBuddy, so the byte weaving stuff, they're providing support for native image. So I think we're getting better and better at all these edge cases all the time. Thank you.
I think there were a few questions in the chat box. Adam's asked, Adam said, excellent talk. How does Spring Native improve on what you have there?
Yeah, so I'm using Spring Native. So in the POM file that I generate, well, let's have a look. I think it's called Spring Initializer, isn't it? Is it Spring Initializer? No, Spring Initializer. There we go. Oh God, I'm typing. So if I use this, I can put in native Spring Boot native, add it as a dependency. I think that only works with, I can't remember. It's one of these 2.67. Anyway, but you can find this stuff out. It's all documented. I can build. I don't know. Let's add web as well. Spring Web. I can build myself a POM file setup. Is this going to work? Yeah. Okay. And yeah, you can see it's got the plugin that I talked about, which is the Spring Native plugin. and then we have to, at the moment, pull those in from like Spring repositories. Yeah, and it provides a very kind of similar setup to the POM file I've been using. So yeah, Spring Native. Yeah, I'm making use of that now. So yeah, it builds on, but Spring Native is basically tooling around Native Image. You know, Native Image is the thing that enables you to build these, like, you know, super fast starting, low footprint binaries, native executables. Spring Native is the tooling that makes, you know, provides the fixes and the workarounds basically to make Spring work with Native Image, because it's like Spring's very dynamic. Sorry, I should look in the chat. Sorry, that was yeah. Has it handle reflection? You have to tell it about it. I think I talked a bit about this. I don't want to go on and on, but you can. Let me. Have I got any of that generated in here? So no, I haven't. But I wonder if I could find that. Would that be in here? Yeah, here's an example. So inside my target directory, here's the reflect.config. This describes any reflection that, like, the Spring tooling knows is going to happen. So we provide an agent, a Java agent, that will capture all of this for you. But a lot of libraries and tooling are now sort of been able to generate this or provide this for you, so you don't need to. And really, this kind of should fall more on the shoulders of like library developers, right? That you don't want to be generating all this time, and the ecosystem adopts it more and more, which it is doing because people want the low footprint and the startup times. A lot of this stuff is, you know, less and less of this is required. But anyway, so there's a lot happening in this particular space, some of which I can't talk about at the moment, but there is a lot happening in this. But in order to support reflection, you need to tell Native Image that it's happening. Some of it can deduce by looking at the code as part of its static analysis, but not always. So that's why you need to be able to tell it. And then there was another question as well, wasn't there? It is, but I just got literally 0 instructions. So so user beware. So let me go and look on GitHub. I'll get you share the, is it that one? I think it was, yeah, Graal containers. I'll share the repo with you. Oh no, I have put some instructions in. I mean, they only go so far. This is basically for my use. So let me, where's the chat box gone? Yeah, let me put it in there, and feel free to copy it. But you get the idea. You just need to run step 0, step 1. I think on the main branch, like, everything's in there, so you can do it that way. Just run step 0, step 1, step 2, and I think you need to run them sequentially in the main branch, right, to build each container. There's not like a build everything script, but you kind of get how it works. And we've also, which might be interesting to you, we also, if you go to Luna, we're providing, I'm writing a lot of labs at the moment, online labs. So if we say, for instance, it's an Oracle platform, but you can go online and close the chat box. You go online and you can, I think I've got a GraalVM Native Image quick start. So I'll share the link for this, but there's a few GraalVM labs on here. It will launch you like a virtual environment with a desktop on Oracle Cloud. It's free to use. You need to create a login, but again, that's like, it's not a login that you'll get spammed with or requires a credit card. It's just the same one as you use for downloading on OTN. You hit the launch button up here, and it will create a desktop, and it will spin up, you know, desktop with tooling on it that will also create a cloud machine with GraalVM and wire everything up. You'll have the source code for various examples. So if I share that one on the chat, that's probably something that's kind of a good way to learn about GraalVM. And give me a sec. And as I said, search GraalVM. We've got something about reflection. We've got a lab all about reflection. We've got some on building cloud applications with Micronaut, various different things. So yeah, that's kind of worth checking out. Just search GraalVM on Luna, and there's a lot of stuff that you could do there. And we're adding new labs all the time. So I've got about another 4 or 5 to write by the end of the summer. So wish me luck. Yeah. So any more questions, or has everyone had enough?
I think that's a lot, Kris. That was really good. I mean, to be fair, most of the code just went completely over my head, but from the few of nodding heads, I am presuming that talk was very good. Usually, when there's like PowerPoint slides, I can semi-follow it.
Right.
But yeah, actually, that was a good sort of departure from what we've previously had, that were quite PowerPointy heavy. But yeah, I think having sort of a live demo or live, coding session, that took from like start to finish, was really good. So yeah, many thanks for that. I will share. I'll share the links later on as well. But yeah, if there aren't any more questions, then we can all have a great evening. But Kris, that was amazing. Thanks very much.
Oh, no worries. Hope everyone liked it, and check out Term Graph so you can get like lovely bar charts in your terminal.
Brilliant. Thanks everyone. Have a good evening.
Cheers. Bye.